A talk about real time, and probably the first thing some of you would notice, it's written Erwin. This has a reason. The reason is the slides are prepared from my brother, and he's supposed to be here, but he must work for his company, and so I have the pleasure to introduce his slides and my talk. Accidentally, I know also a lot of real time, so it shouldn't be the problem here. Okay, uh, let's start with the obvious first question. What's real time, and what's the difference between concurrent and real-time programs? In the beginning of the software development, there were sequential programs, like everybody remembers these big, huge mainframes. They were just able to make one thing after each other. And so the execution is predetermined, and the results are independent of the execution speed. This is quite easy to catch the figure. And also, it's quite nice, you can often analytically verify of the correctness. Concurring programs, this is the typical situation of today's operating system. They execute multiple programs in pseudo-parallel. I mean, pseudo-parallel is like, it seems it's parallel, but it's not parallel. Of course, we have one CPU, so the CPU must give a time slice to this process and then give a time slice to another process. And so we have the feeling of parallelism. But as today's operating system try to be quite fair, it will happen that some program gets a specific amount of time, and afterwards the operating system looks at it and said, well, okay, there is another low priority task that hasn't got a time slice for quite a while, so why not give them the next slice? This is quite good, and in most of the situations it's comfortable. But for instance, the results of concurrent execution is dependent of the execution speed. I will come to this later, but it's not like sequential programs, and it's not like real-time programs, because in real-time programs there is a deadline, and each real-time operating system satisfies this criteria, giving a task after an event occurs within a deadline, a guaranteed reaction to this event. I mean, it doesn't sound to something special, but let's have a look at it a little bit in detail. So, as I've said before, real-time programming guarantees the reaction on an event before the deadline. Real-time isn't necessarily fast. Most of the times, real-time It's like real time and embedded and fast. And no, real time just means there is an event, and before the deadline is reached, there is a reaction. Every time. Not most of the time. Every single time. The time limit, of course, depends only on the application. For instance, the time limit for switching a railway, the embedded device for switching two railways to each other could, for this device, real time could mean 3 seconds. Actually, it's not very fast, 3 seconds, but it means it's satisfying if the reaction occurs in between 3 seconds. In automotive industry, so with cars, modern cars have plenty of computer stuff inside. This could be 10 milliseconds or less, depending what this device is doing. So, real time means the computer reacts in time. Okay, we have different types of real time. Of course, the obvious hard real time. Hard real time will never fail. I mean, soft real time may fail and will. For a typical example of soft real time, look at your mouse cursor. If you move your mouse, you see the mouse cursor moving also, and most of the times it behaves like this. Sometimes it flickers and the computer does something more important in his opinion, and yes, then it fails. But I mean, in case of a mouse cursor, it's not that catastrophic, but for hard real time, imagine a meteor, a comet, and you have a device where you want to take photographs when a meteor or a comet is touching the air surface. So you have a trigger, and this is just a box which says, okay, wow, here it is. And then you have the photograph unit, which gets this event. And this is where hard real time comes in. If the photograph box doesn't react within the deadline, you will miss the shot. I mean, there are other examples of real time, like moving a car. But in case the difference between hard real time and soft real time is hard real time will not fail. Soft real time may fail and will. Okay, for soft real time, as I've already mentioned before, you can use your operating system. Mouse task is a typical soft real time task. Well, for hard real time, you need something more specific. You need a real time kernel. Most of the times, real-time kernels are associated with embedded systems, but embedded isn't real-time, but most of the times embedded devices. For instance, your DVD player at home has a real-time operating system. Your digital television receiver, if you have one at home, it's a real-time system. And so embedded is a special purpose computer system which is completely encapsulated by the device it controls. Nothing really beside this is special on an embedded system. It's just fit into the special purpose. It doesn't mean that it's fast, or it's just as fast as it has to be. So real time, that's the good news, can be achieved on every computer system with the appropriate means, like what is your deadline, and so let's see how we can achieve this deadline. Okay, to begin, become a little bit more detailed, as a forecast, we will have a look at the Linux RTE kernel extension, that is a Linux real-time kernel on top of Linux, of course. And so the problem is that Linux is a typical concurrent system. You have no deadline guarantees. You have especially people who use the Linux for audio performances would notice you have strong variant of execution time. This is especially if you do something with audio quite bad. And so how do we real timing of Linux? Okay. You have the tasks which are going to get executed. The scheduler is that part of the operating system which is supposed to do that. ISR is the interrupt service dispatcher and the interrupt controller, of course. So, how we put real time on top of it? Basically, we take the interrupts, the events, which get fed from hardware, and replace our interrupt scheduler with our real-time scheduler. There we have our real-time task, which are completely independent from the normal tasks. And of course, Linux is running as one low priority task in the real-time system. Okay, how can we do this? To know how we can implement a real-time program or hack our digital television receiver, we must know some few things about what is a task. I mean, a task in this context. A task is an independent thread of execution. It may contain functions or uses functions, but a task is not a function. It may be synchronized, and of course it will most of the times communicate with other tasks. And in case of real time, it may be non-preemptible, preemptible, or time-sliced. It may be non-preemptible means nobody, also the operating system, is allowed to interrupt this task until it's finished, or it gives away the time slice by itself. Preemptible is the opposite, means okay, you can interrupt me. And time sliced, we will come to this later, is a specialized thing in real time you do when you have no interrupts. I mean, We can do this later. Okay. A task has, of course, a priority. Everything is based on this priority. It's not like the Linux nice level. It serves a similar function, but the priority is a criteria if a task gets scheduled or not. It has some states, of course. Most important ones are blocked, ready, and running. And it's maintained by the real-time kernel. So basically a task is an endless loop. It blocks if it wants something from outside, I/O. Yeah, it's set up by an init function. In case of RTI, you insert the kernel module. This is the start of life of a real-time task. And it's made of you see the task is made of disk data. This is the data segment, the code, the stack, and some real-time operating system internal task control block. Of course, what's in this task control block? Most of the time there is, of course, the ID of the task, sometimes the priority, but it's mainly business of the real-time operating system, what's inside. Okay, let's go to scheduling. As I've said before, a task can be preemptive or non-preemptive, and periodic or not periodic. Periodic tasks, as you see in this picture, gets involved every 5th time slice. This is a little bit, this is a little bit simpler than it actually is, but I think it explains the picture. Periodic task, like I've said time sliced before, you see the periodic task gets involved every time the time is over, and so it interrupts the preemptive task, runs a little bit, and then gives back control to the preemptive task. So as we see around 10, there is another high priority non-preemptive task. Yeah, and the periodic task therefore gets involved a little bit later. Depending on the timeline, this is a good or a bad thing. So the interrupt service routine is one of the core concepts, one of the important concepts of a real-time system, because basically it's the function where you get control out of order, which means an interrupt occurs, you can react to it, or the real-time system can decide to ignore it. But the interrupt service routine is a very small part which just looks which interrupt happened, what's the current state of the system, will it return to the task after the interrupt, and well, what priority is the task currently running, and then decide what to do next. So, in case of real time, we have a task We have an interrupt service routine. Okay, now we are able to react on external events. We have the possibility to activate or deactivate a task, but right now it's a little bit boring because we have no way of communication, we have no way of synchronization. So this is where the message queues comes in, and message queues are for inter-task communication. Usually, in real time, you're using fixed length data. Usually in real time, you do as much as possible at design time. This has a reason because you want to get this system deterministic. The more you know at design time, the better it will actually go. So fixed length, it sounds like, so real time is really, you must know what you're doing.
In wenigen Minuten wird der Gewinner der Suchaufstellung am Wikipedia-Stand bekannt gegeben. Vielen Dank.
Okay. So in a few minutes we will have a winner for what? Okay, so the message queues. In Artile Linux, we have every flavor of message queues you want. We have mailboxes, we have queues and pipes. In other systems, like Pesos is an embedded real-time system mainly used in consumer environments like DVD players. Probably you have one at your home. But common to all this implementation is you have a maximum size of elements which can be queued, and you can use this message queue for sending data. So, but so I'm wanting to sending data to the screen. Well, in this example, you see two tasks. One simple, something nice to display to the user, but the results aren't that nice because they each get a little time slice, and well, that won't work. So we need more than message queues, we need semaphores. Semaphores is a principle, it's like a token. In the history, on railway tracks, there were, on parts of the railway tracks, there were only one railway. So how to, and you know, telegraphic communications wasn't that good at this time. So they had the problem how to not to crash two trains into each other on this single line. And of course this was easy. They used a token. At the last station, before it went to one line, there was a stop, and either the officer had the token there, and the token was given to the train operator, and with the token, the train operator crossed this part of the railway, or he has to wait until the token arrives. So you are passing tokens. As soon as you have the token, you are allowed to use one device or whatever you want to use. So here is our token, and task 1 and task 2 in this example both want to get the token. Well, task 1 is in this case faster. Task 2 gets a message, well, your token is not available, and it blocks. So task 1 prints hello world. Task 1 gives this token back and unblocks task 2, which can then print good evening. And then, of course, like every good program, it must give the semaphore back. So semaphores are used for inter-task control communication. You can protect your resources with it. Depending on the implementation, there are counted semaphores. There are some, I think I can imagine some examples where counted semaphores are useful. Most of the times you don't need it. If you want to take a semaphore and you're out of luck, this will block your real-time task. Of course, you have to give it back. Sometimes in case of inter-task control communication, you're speaking of mutexes. Basically, it's a semaphore. It's just it's slightly different, but in this case, it's the same. So, okay, what else do we have to have a working real-time operating system? Of course, we need a timer. Single shot events or periodic events. Sometimes the timer is the only interrupt which is allowed in a real-time system. Then you're doing something from top button. You say, I don't care about hardware interrupts. I don't care about whatever device wants my attention. I just use a periodic timer, and this is my only source of interrupt. And this is time triggered, as I've mentioned before. And in case you know exactly at what time you must react or not, it may be a clever solution than having hardware interrupts, because it's not a matter of how quick or how efficient your processor is used. Yeah, also real-time programming doesn't mean you're using your processor efficiently. It's not, I mean, yeah, you should do with the processor what you want, and you should have sufficient power to do it. But real-time systems, most of the times, is designed to be utilized not more than 70%, and it will be utilized at 70%, even if it does nothing, almost nothing. The rest of the rest, like the 30%, are only for unexpected, non-deterministic behavior, especially if you try to make real-time on a architecture like the x86. You need quite a lot of buffer because it's quite non-deterministic. So the timer is one of the most important devices when it's going to go about real-time. It's used for delaying, it's used for waiting, and yeah. If you wait for something, it blocks, of course. And Yeah, another thing that will make real-time programming a little bit more comfortable. You have a user kernel space communication, because RTI, the tasks, as I've mentioned before, are placed in kernel mode. That's good on one hand, and you have a libc, a specialized libc, that life is a little bit easier there. But most of the time you just want to do a specific task in real time and make the rest of the calculation, the rest of the presentation or whatever in user space, and there you can use whatever library you want or use unreliable transport mechanisms like TCP/IP. So for this reason, RTI provides a FIFO, that means it's a ring buffer, basically with first in, first out, and shared memory access for user kernel space communication. So, I think we now have the basics of real-time programming. We have tasks, we have mailboxes, message queues, data which can be sent from one task to another. We have the semaphores, which we use to control the data communication, to control reaction and reservation on external devices. So, sounds easy, but there are some more obstacles. We have enough of the API to do something useful, but there are obstacles. And one of the typical obstacles you will have to face is priority inversion. And usually a real-time task never gives time to a lower priority task if there's a higher priority task ready, so waiting for execution. So basically priority inversion should never happen. But if in this example you see there is a resource and task 2 takes this resource. Then there is some periodic event of another real-time task. And task 1, which has a higher priority, is executed at around 6. But task 1 needs a resource currently reserved from task 2, and therefore it must block and let task 2 finish. And you see that the area of priority inversion, there are lower priority tasks being executed of the real-time kernel because the higher priority task cannot get this resource. So usually priority inversion is something you get when you're making design flaws, like messing around with resources used by different tasks. There is an example, actually, a very nice example. A tank had some kind of priority that the real-time control software of the tank had some typical example of priority inversion. And the screen, there was some debug output, and the first of the, how you call these things on a tank where it's moving, I mean the chain, yeah. The chain is connected to two engines, front and rear. And the two engines, of course, must run synchronized. And in case of the tank, the chain broke because the engines were running out of sync, because one of the engine was starting, then the other engine, of course, should start before the deadline is reached. And the first engine was writing something to the screen. And exactly at this time, there was a periodic event where at the screen there's written the time of the day and some temperature stuff. And actually the screen functions were very bad written. So the screen task was actually crashing and didn't give back one semaphore. I mean, waiting. The task which was responsible for displaying the time and the current temperature was did crash. Therefore, it didn't give back the resource, the semaphore of the screen, and therefore the second engine couldn't start because it couldn't get the screen, so it blocked and the chain simple fall in small parts. So this was very complicated to find, because at first they had no idea what happened, and then they figured out, well, every time there is something in movement and there is this temperature display, something bad happens. And this is called priority inversion. So priority inversion is bad, but it's a design flaw, and you should avoid it quite easy. So another pitfall before I finish is typical deadlock. You know the philosopher's problem? You have 4 philosophers, and left of you is a fork, right of you is a spoon. And yeah, you look, if it's something left to you, you take it. And then you look, if it's something right to you, you take it. If not, you wait until it's there. If all 4 philosophers make this, well, they won't eat anything. So the task block because of mutual reservation of resources. Again, system design. You can avoid this, but for instance, in this case, you must have a look, how can we solve this with one semaphore? You have 2 semaphores here for each philosopher. I mean, you have 4 semaphores. For each fork and spoon, you have 1 semaphore. But you could solve this with 2 semaphores. Yeah, and here's the explanation why time trigger systems sometimes make sense, because in high load situations there is something called interrupt storm, and of course every interrupt takes a little bit of time, and if you have for a certain event tons of interrupt, you have something like an interrupt storm, and this could lead to situations where nothing goes on at this point, because the system just serves acknowledging interrupts. You can fix this if you just use time-triggered slots, and then look, oh yeah, okay, my one I/O resource was just behaving like wild. Okay, well, forget about it and look at the other things. So time triggered has usually you give away a little bit of performance, but you can avoid high load scenarios. Okay, as I have begun my talk a little bit later, I must skip the last part. But of course, what is in security situations where real time is used in cars or in aeroplanes, you have some additional protection, and this also involves that the system is checking if everything is really in time, within the deadline. I mean, because when we are talking about the deadline, it should never occur, but in case of a car or in case of an aeroplane, it's still good to verify this. So you have some additional timestamps on each message. You have additional timestamps on each task to check if it's in between the deadline or not. The tasks, of course, are separated from each other. Most of the time in real time, especially Artel Linux, you're all in kernel space. I mean, that's a lot of fun, but you could do to other tasks whatever you want, and in case of an aeroplane, it won't be that good idea. So they have additional protection features, and yeah, fly-by-wire is one of these typical examples which we can use for additional protection. Also, in this case, you always use fixed time slices. You trash everything about interrupts. You don't need it. You need fixed schedules. And if you want to do something in real time, probably you could start using Artel Linux and getting one of these shiny digital television receiver cards and play a little bit around, because you could possibly attack the encryption of the television broadcast with a real-time task. Everything else would fail, of course. Probably you will fail too, but if you use real-time, you have at least a chance to react to the decoder card within the time limit, and so the show goes on and you have an additional chance to decode it. So real-time is more or less in many devices you have at home. Real-time is very common in your electronic devices all over, and it's not that hard to use. But yeah, remember, real-time means to react within not reaching the deadline. So to be real-time in this talk, I must finish right now.